F-35B, engineering marvel of the skies. The F-35B is widely regarded as the epitome of advanced aircraft engineering, combining the capabilities of the F-16, the B Harrier, and the B-2. This stealth fighter plane is a true jack of all trades. Drawing from Lockheed's previous stealth ventures with the F-22 Raptor and the F-17 Nighthawk, the F-35B boasts cutting-edge sensors and computer systems that allow for seamless information sharing among allies without compromising stealth. Pilots are provided unparalleled situational awareness through a heads-up display on their helmet visors, enabling a cohesive and efficient fighting strategy. One of the boldest features of the F-35B is its ability to transition from horizontal to vertical flight with a simple push of a button. Utilizing directional thrust and a powerful vertical turbofan engine hidden within its body, the F-35B can land vertically on small amphibious assault ships used by the U.S. Marines. This remarkable engineering feat, however, poses significant challenges. Designing an airframe that encompasses all these capabilities is an extremely intricate task, demanding meticulous attention to detail and trade-offs. Contrary to common misconceptions, stealth technology does not aim to render an aircraft completely invisible. Instead, the goal is to delay enemy detection for as long as possible. By minimizing the strength of the return signal, stealth design reduces the range of enemy radar stations, creating opportunities for aircraft to slip through undetected. For fighter aircraft like the F-35B, stealth provides a critical advantage by allowing them to detect adversaries before being detected themselves. There are various mechanisms through which radar waves can be reflected, with the most significant being spectral return or regular reflection, similar to a mirror where the angle of reflection equals the angle of incidence. To avoid such reflections, it is crucial to steer clear of large flat surfaces and corner reflectors created by surfaces set at a 90-degree angle to each other. The tail planes, including the vertical and horizontal stabilizers, are particularly susceptible to creating corner reflectors. To mitigate this issue, the F-35B replaces both stabilizers with a tail, similar to the F-17 Nighthawk, which acts as both a rudder and an elevator, optimizing control authority. Designing for stealth also involves minimizing sharp edges, which cause radar waves to scatter in all directions. By employing separation techniques and incorporating serrated edges on access hatches, the F-35B reduces edge length and scattering, thereby diminishing the return signal strength. The aircraft's engineer intakes, cleverly positioned on either side of the fuselage, provide aerodynamic advantages while preventing radar from bouncing within the intake and back to the receiver. Additionally, specialized radar scattering tape is applied to the aircraft's surfaces, gradually decreasing its electrical conductivity and dispersing radar waves over a longer distance, further reducing the return signal. The F-35B's surface is composed of a specialized radar-absorbing material that can absorb a wide range of frequencies, including those used by advanced surface-to-air missile systems like the Russian S-400. Moreover, the aircraft features a ridge on its circular nose cone, breaking up the circular shape and preventing radar waves from traveling around the outside and straight back to the receiver. These and other stealth design elements contribute to the F-35B's impressive radar evading capabilities. The F-35B's transformation from horizontal to vertical flight and vice versa is a spectacle in itself. A clutch transfers immense power to the lift fan, generating significant vertical thrust and creating a low-pressure zone above the aircraft. Carefully engineered mechanics, including the three-bearing swivel nozzle, allow for smooth transitions and precise control. Bleed air from the main engine bypass is used to control, and to make matters worse, that space is used for internal fuel tanks for its variants. Making the lift fan as light as possible was pertinent to making the F-35B valuable in the battlefield. The fact it only weighs 1.2 tons is astounding. It contains two counter-rotating titanium bliss explicit, meaning the blades and disc are all one single piece instead of the traditional alternative of creating a disc and attaching blades through dovetail connections. This improves efficiency and eliminates a potential site of failure in the connection. This is an astounding feat of manufacturing, and the first stage fan takes it even further. The first stage blades are hollow to safe waste, where the F-35B truly comes into its own, however, is in its modern suite of sensors and computers all feeding into this. The heads-up display incorporated into the pilot's helmets, traditional heads-up displays like those of the F-16, are incorporated into a panel in the cockpit. A panel which the pilots can't see when scanning their environment. Situational awareness is everything in the heat of combat, and this helmet does everything it can to keep the pilots informed, even giving them X-ray vision and night vision information from a suite of sensors around the plane feed into a central computer where it is processed and displayed through a projector inside the helmet. Inside this transparent faceted box, underneath the aircraft is a suite of sensors, but those are not your typical windows. These windows are made from a notoriously expensive gemstone sapphire, one of the few materials that is both hard and durable, but also transparent to a broad range of electromagnetic wavelets from ultraviolet to infrared. However, the radar antenna hidden inside the nose of the F-35 is the most important part of this electronic system. This is a scanned array radar that works very differently to traditional mechanical radar. Phased array antennas have hundreds of tiny antennas. We can see metal plates set in rows in the F-35 phase array antenna. The metal plates have slots cut into them, and each and every one of these slots is an antenna 1600 in total. This allows the Phase 3 antenna to steer its radar using constructive and destructive interference. If two antennae release two radar waves at the exact same time with their peaks and troughs lined up, it will result in constructive interference increasing the amplitude of the radio wave. However, if the radio waves are set 180 degrees out of phase, matching the peaks to troughs, it will result in complete destructive interference, canceling out the wave completely. This is how noise-canceling earphones work. They listen to the background noise and then release a canceling sound wave to create silence. Phase 2 ray antennae use this phenomenon to steer the radio waves, preventing the radar from becoming a joint beacon leading enemies straight to us.